Measurement and significance. You've probably heard of this and dealt with it before in previous classes. It'd probably just be pretty quick, down and dirty with maybe a good explanation. Because this deals with how do you tell me what answer you get when you do a problem, right? So all those numbers that we get in problems, you need to assume that those are going to be measurements that have been made by somebody taking some sort of measuring device. And then they're describing to you in words what's going on with that problem. Every device that we might be given, right, has a different inherent ability to measure, whether it's a balance to measure mass, a ruler to measure distance, or a spring scale to measure forces, or a watch to measure time. The inherent ability of a device to make measurements is a property that's known as precision, right? It's the mechanical ability of the object and how it's made to measure or produce an outcome. Right? Our ability to use the device properly, right, is a factor that we call accuracy, right? That's the human ability to use the device. Probably the best example with precision and accuracy comes from the field of like high-powered rifles, high-powered rifle shooting. So if we look at, there are certain rifles that are produced, and you pull them out of the box, and there will be a guarantee that that object will put 3 bullets when fired downrange at 100 yards within a 1-inch square. All right, so if you get one of these rifles made by various different companies or handmade by certain gunsmiths, you'll pull a target out of the box, and there'll be a target in there that'll show you what your rifle was able to shoot. And here you can see those 3 bullets have been impacted the target, right, at some point where the rifle was clamped in a stand, everything was kept the same, and it fired those 3 rounds, and they were all guaranteed to be within that 1-inch group. Now, accuracy then would be somebody's ability to take the sights on that rifle or put a scope on that rifle and adjust it so that the 3 bullets might impact, for example, there and there and there. Right now, that might be the best that a person could actually do with that rifle if they're not skilled if they don't have skills as a marksman, right, in marksmanship. That might be the best anybody could do, which is still not really bad in terms of rifle shooting. But obviously, the purpose then would be for the ability of some person to take that rifle and adjust sights, do whatever it needed to do, follow all those principles of marksmanship, and impact 3 rounds inside that 1 little inch circle in the center of the target. So obviously then being able to use the rifle properly, right, to use the precision of the rifle and put it where you want it is a highly developed skill. Now obviously the stuff that we use in science, physics to measure distances, etc., don't involve all that type of mechanical precision that something like a rifle does, but that's really the idea behind the difference between precision and accuracy, right? You want to be able to use the piece of equipment properly to get the most out of it. All right. So regardless of what device we use, right, to measure in science, there's always going to be some human or mechanical error involved when we take measurements, right? And those errors are going to be present whenever we record a measurement. And then if we use that measurement to calculate some quantity like speed or volume or area, the errors that come with the measurements are going to be compounded into our calculations. If we look, for example, at these 3 different rulers, ruler 1, 2, and 3, and we look at distance A and distance B, and we think about distance A and distance B being the length and width of some rectangle of paper. First of all, if we look at the rulers, right, we look at ruler 2 and ruler 3, and they are both seem to be calibrated in 1 centimeter increments. And we can see that one of them is a little bit better than the other one. If we look, we probably see a big error right here and an error right here between 5 and 6, 6 and 7. We should be able to see that those things don't appear to be made correctly. So ruler number 3 is not really precise. It's not a precision made ruler. Looks like somebody just put some tick marks on a line, right? But we're still going to look at that and measure, because that could be something that we get, and we have to look at that measurement. So the first thing we want to look at, and then we can look at ruler 1 then, and see that ruler 1 is not only calibrated in centimeters, but also in tenths of a centimeter, right, which are millimeters, all right? So every time we use a measurement or make a measurement with one of those things, we're going to have to estimate. So if we looked at object A, for example, and we looked at ruler number 3, if we look down there using ruler number 3 and we read that instrument, I might say it's 6.6, you might say it's 6.5, right? Neither one of us would be wrong. My 6.6 would be my estimation of the line is actually a little bit more than halfway between the 6 and the 7, right? And yours might be, well, it looks exactly halfway. Neither one of us is wrong. That's just the measurement that you make, and that difference between what you see and I see, that's the human error. That's the accuracy factor. Then if we looked at ruler number 2, right, we might both look at that and say, I say it's 7.7, you say it's 7.6. Neither one of us wrong, just my estimation and your estimation. All right, then, however, if we look at ruler number 1, we look and see that it's 6.1, 2, 3, 4, 5, 6, 7, and it's not quite to the 6.8. So I might say 6.79, you might say 6.78. Neither one of us wrong. Somebody else might say 6.77. Even if somebody, if somebody said 6.80, I might be able to say, well, you can see it's obviously not quite at that point, but even they wouldn't be wrong. It would just be their estimation. So looking at the length of object A, right, using ruler number 3, I said 6.5. That's really, when we record that measurement, that's saying, well, it's somewhere between 6.4 and 6.6. That's my best estimation. When we look at ruler number 2 and I say 6.7, right, it's really saying it's somewhere between 6.6 and 6.8. Then when we get up to ruler number 1 and I say 6.78 or 6.79, that's really saying it's somewhere between 6.78 and 6.80. Obviously, ruler number 3 is much better at measuring. It is made to measure better because it's got those additional tick marks. All right, look at the same thing with ruler number object or length B, and we'll read those measurements and see with ruler number 3, it's 4.4. You could say 4.3, no problem, right? Ruler number 2, it looks to be, 4.5. You could say 4.4 or whatever. And then ruler number 1 looks to be 4.48. All right, so just almost halfway. All right, so if you said 4.47, 4.49, no big deal, right? Your estimation and my estimation. But when we record those measurements, we're saying that 4.48 is between 4.47 and 4.49. That's our best guess. The ruler number 2 between 4.4, 4.6, ruler number 3 between 4.3 and 4.5. Now, each of those values then is going to have a certain amount of error associated with it. So when I look at calculating with my measured values, my recorded values, I calculate the area, which is the length times the width, right? I get 28.6 using ruler number 3, 29.25 using ruler number 2, and 30.4192 using ruler number 3. If, all the measurements were actually closer to these minimum values from my 6.5, they're on the bottom side, then ruler number 3's area becomes 27.5. Its maximum, if they were both, maximized errors, 29.7, 29.04 to 31.28 for ruler number 2, and 30.3066 to 30.05320. Right? So obviously ruler number 1 allows me to get a much better look at the true value because it is made much better, right, to make measurements, right? But if we used ruler number 2 and we had this value of 29.25, that is a correct value. That's the best we could do with ruler number 2, all right? Now, when we get that answer, looking at using ruler number 1, right, because it's obviously made to measure things more precisely than ruler 2 or 3. When we get our answer in our calculator, 30.4192, right, how would we express that answer to somebody who was asking us, hey, what's the area of this paper? Because there is a right answer, right? Well, if I looked at 30.4192, I would probably say, well, the measurements that I made with ruler number 1 were to the 100th of a decimal place. So I'd probably round my answer to the 100th of a decimal place, 30.42. And then there's a lot of different ways I could use to describe, well, how much air is involved with that. I could use plus or minus 0.05 centimeters squared, right, where I'm expressing the possible air as half of the smallest decimal place that's included on my meter stick, and this should probably say 0.005 because the last decimal place was the 0.01, so I'd want half of that, 0.005. I could do some rigorous statistical analysis and say 30.4 plus or minus some, you know, how I calculate standard deviation and a bunch of other stuff between the air. I could do some stuff that you might learn in a physics class right at the college level. Or I could say 30.4 centimeters squared, and I could just use sig figs. Right now, significant figures really are just one way of expressing our answers so that we take errors into account. Right? If I tried to use 30.4192 and report that value as the correct answer, my ruler, right, is only good to that decimal place. And that's an estimation. That's where my error is. If I go 2 decimal places more, I'm trying to say that I know the value, the correct answer, 100 times better than the ruler can measure. Right? And that's really not something that we want to do. It's not feasible. It's not correct. Right? It'd be the same thing if I told you to get in your car and drive 25.325 miles using your odometer, and I want you to stop at exactly that distance. That's impossible for you to do in your car because your car's odometer probably measures to the whole miles, or if you use the little trip feature, you can probably get to the 10th of a mile. So the best I could do would be 25.3 miles, and even that would be an estimate, right? Unless you start your trip exactly, hit your trip timer exactly when you start pulling and rolling the car out. That'd be the only way. All right, so significant figures is one method of accounting for error, right? We should be familiar with the idea that when we use multiplication or division to calculate, we express our answer to the least number of sig figs that are in our problem, right? So when I look back up at my data up here, right, 4.48 and 6.79 both have 3 sig figs, so I should be 30.4 for my proper answer, right? And then if I'm adding or adding or subtracting, I want to express the answers to the last decimal, the smallest decimal place that both things have in common. So if I looked at like 35.27 plus 5.3, right, I would have 7 and 5, 0, 1. So I'd have like 40.57. So my answer would be 40.6 because that's the decimal place that they both have in common, the 10th place. All right, and you should be familiar with that. If you need a refresher on how to determine the number of sig figs in a problem, you could check out, just search Pacific Atlantic Rule for sig figs on Google. You'll find a bunch of sources on that research. And that's the easiest way to deal with sig figs, to determine sig figs. There's some people that use a whole bunch of different rules that get all chaotic and crazy that you forget. If you just follow the Pacific Atlantic Rule, you won't have any issues. But for us, we really don't have to get to sweat it too much, right? A lot of times in physics classes, problems are notorious for saying something like a 20 kilogram mass, and they'll write it as a 20 kilogram mass, slides down a frictionless incline a distance of 3.35 meters. And then they want you to find acceleration, or they want you to find a value of the force, or something from it. And here this has 3 sig figs and this has 1 sig fig, and so neither one of those is really paying attention, because they don't get all hung up about, oh, it's 20 point kilograms and that means that's really between 19 to 21, right? They don't really worry about all that in physics like they did in chemistry, or they will in chemistry. So it's something you don't have to worry about as much, right? Really, if you use 3 sig figs on most of your answers, you're not going to have any problems. I'm not going to be looking to, and you know, they'll talk about some error stuff on the AP exam by the time we get there, and sometimes they put stuff this way, but they'll ask you what possible values are, and we'll go over that before we get there. As we get into later in the year and we start reviewing. For us, the big thing becomes, how are we going to limit or minimize the amount of errors when we do lab? And for that, there are several different things we can do. Right? First thing we can do, we can always conduct multiple trials of a measurement to assure that everything we get, all our measurements, are as consistent as possible. So we don't have a possibility of, we read something, you know, between 5 and 6 and we thought it was between 4 and 5. Right? So we make multiple trials, right, to make sure our data is as consistent as possible. Right? We use graphs of data points to analyze a trend in the graph of several different trials, right? With the best fit line. The best fit line is going to be a way that minimizes error, right? And the error of every measurement, so that we get a best look at the actual values, right? At the true value of the trend, right? A note, calculating the value of each set of measurements and then averaging those values really makes every error that you've inserted in there by measuring, it makes it grow, right? So you get a much wider spread and you begin to lose where the average is, right? We want to try and do everything we can to make errors smaller. If you, for example, multiplied in our density lab, if you divided the mass by the volume, mass by the volume, mass by the volume for the 4 blocks and averaged those values, right? The mass has an error, the volume has got 3 different length errors, length, width, and height, that are all multiplied, that are all going into making the error of possibility of error bigger, and now you've just used that bigger error 4 times and tried to average it, right? The best way to do that is to look at using a graph, right? So for our lab the other day, we should have the density for wood type 1, right? I plotted those points, calculated my volumes, right? And then had a best fit line. And you can see here that data point number 2 sits slightly probably above that best fit line. Data point number 3 is definitely a little bit above that best fit line. And data point number 2, if I extrapolate that line, we see that it's a little bit below. So by using the best fit line, we kind of take all those inherent errors in each data point and we average them out. So now this, if I have, right, this equation, right, I have mass on my y-axis equals mx plus b for my equation, right? Well, mass is on the x, on the y-axis. Volume is on the x-axis. The slope of that, right? The slope of that graph would be delta y over delta x, which would be change in mass over change in volume. Density is equal to mass over volume, right? So the slope of this graph gives us our density. All right, now the 0.454 is a little bit higher than the average you get by calculating all the volumes and then finding the mass of each, or the density of each block and averaging it. You get like a 0.42 value, right? But here you get a 0.45, which is much closer to the correct answer. And that's what we want to make sure we do. We're going to do a lot of analysis of graphs involving various quantities, right? Initially, we'll be looking at a lot of slopes of graphs that are position versus time and speed versus time. And that's what we're going to spend the rest of this week and part of next week talking about initially is the motion of an object in one dimension and how we produce graphs and describe that motion using graphs. So hopefully that answers a question about labs. If you need to refresh your lab or redo it, or make your graph again and with this understanding, feel free to do that and resubmit. And then if you have any questions about it, you can let me know during, just email me and let me know. And if we have to set up a session for like Tuesday afternoon to go over it, we can. Y'all have a good one, and we will talk.